So, hello and welcome to. So, this is lecture 5, is what I have in my notes, if I have my notes open. So, yeah, sixth. I actually don't know how you say that word. 6th stream, 5th lecture. I'm going to keep saying it every single time just to point out how stupid indexing at 0 is. This is why I do it every single stream, by the way. Where we are looking at momentum and impulse. So, previously, on last week's episode, we were looking at something else. Work, energy, and power. That was it. And those were basically a way of sort of quantifying sizes of force for a certain amount of work done. That was essentially saying how much force was applied and what the result of that force was. Yeah, I was wondering, Tech. It's like, I don't know what that is. Similarly, energy is arbitrary thing. Specifically, we looked at kinetic energy and potential energy and a way of translating or transferring force into energy. And we start going down a physicsy rabbit hole, so I hid. But essentially, we're talking about the resultant effect of applying a force to something. If something is under force, it's probably going to move because of it. Historically, we were looking at moments, which is the sort of quantifying the rotational effect that a force has on a body. But a lot of this is coming back to causing motion, right? Going all the way back to lecture 1, I think, which was kinematics of things are moving. Let's describe it mathematically. This is a further extension of that. So in particular, so in particular, for any object in motion, it will have momentum. And I'm going to do a little asterisk there, and I'm already over my name. So, over my face, so I will do that. It will have momentum. And the asterisk is there because specifically momentum is coming from so if an object has momentum, it has to have mass. A massless object does not have any momentum. Today is the ADHD lecture talking about impulse and a distinct lack of momentum. Sometimes too much momentum, but in the wrong direction. When that hyperfocus takes over and you just kind of veer off in a different way. So, momentum slang wise, or not slang, but like sneaks into vocabulary quite a lot.
Hello, cat. Fuck off.
Thomas I just subscribed.
Forgot that
Nose
happened.
wave DDA. How's it going? First stream
Cannot
I've
speak
caught in
Welsh.
2025, and on the day we got confirmation that physics at Cardiff isn't totally screwed yet. How's it going, cat?
Thank you, Thomas, for the 44 months. Bloody hell. Nos eitha. It's going good. I'm tired. We are doing some mechanics. I saw the news about Cardiff, though, with the, what is it, like 400 redundancies that are being introduced. Glad physics is surviving. Worried about maths. Special sub sound, yeah. It's stupid. I feel like changing it. Like, if I had, I owe you, I didn't listen to it yesterday, I'm sorry. I owe you a proof read. But yeah, it's good. It's good. Redundancies? Is that not what I mean? Yeah, being made redundant. Basically, universities in the UK are having a bit of a financial crisis because the world is having a bit of a financial crisis, and lots of universities are cutting down on staff and having hiring freezes and spending freezes. And I had a BBC alert that was like, Cardiff is... I wonder if it's still there. Cardiff was the most recent one on the list to basically say that they're cut 400 jobs. Cardiff University has confirmed plans to cut 400 full-time jobs amid a funding shortfall, which is not great. We don't love that. Yeah. Not that we're all going to end up teaching on Twitch, but I got a mail about spending freezes too. I'm curious if my PhD contract still goes through. I think everyone that is currently on a position should be safe. Hopefully, unless you're in America, and then that is a whole other system that is terrifying. 400 academic FTE losses, several school mergers on the table, believe that. No word yet on non-teaching and non-academic pro services. Yeah, professional services is gonna be scary to quantify, because with the teaching you have like number of students can quantify how much money you bring in, and with research grants can quantify how much you bring in. Is everyone on the in-between that universities are shit at acknowledging how much work they actually put into the whole system. Pretty sad to hear studying Cardiff, so same to see some of the staff go. I know, right? Also, so did I. That's so cool. Yeah, hopefully. It's a scary time. In Germany, I have a permanent position on the PhD, it would just be different. So also different budget. Ooh. Best of luck. Best of luck. Thomas, have you changed your name colour? Because it is an ever so slightly different shade of blue. But it's almost more teal-y green now. In my head, it was quite a bright blue. Shush. Ah! You heard nothing. I'm a professional streamer. What? Aw. Not intentionally. Okay, who knows? If they merge physics and chem, I bet we lose some lab techs. Yeah. I wonder if maths and comp sci are going to merge, given that they are already in the same building now.
Back to work, everybody. Work.
That is so loud in my ears. Oh my god. Okay. I have no idea where we were. What do I have in my notes? Okay. Any object which has a mass in motion, it will also have a momentum. Momentum is a quantity... Spell, please. Which... measures the drive an object has. Mathematically, it's given as... I'm going to write mom a lot to mean momentum. Is mv, which is an object's mass times its velocity. Okay? And this is then measured in kilogram meters per second. So kilograms times meters per second. Kilogram meters per second. Which, those of you particularly keen will notice that kilogram meters per second squared is a Newton. So it's Newton seconds. Yeah, shut up. It's close enough. So, it is also given as... so momentum can quantify how much force may be required. How do you spell? To bring an object to a stop. Okay? So the more momentum something has, if you think about it in terms of how we use it in language, if something has a lot of momentum, it's like going either at big speed, or if we think of like freight trains have a lot of momentum, it's big thing going kind of slow, but like one of those quantities is big. Big thing going fast, massive amount of momentum. Big thing going kind of fast, or like average speed, still a lot of momentum. Little thing going really fast, a lot of momentum. But fundamentally, it's a sort of measure of how much effort is going to be to stop it from moving, or like how much effort it has going forwards. What if an object has a mass of 0? Does it have momentum if it's in motion? Outside the scope of maths. Breaks my equation, don't like it. Essentially, no. It's their tendency to want to keep going where they're going. Yeah. In particular, if you think of Newton's first law, bodies in motion stay in motion, bodies at rest stay at rest. It's that sort of thing of like a force is going to mess with that. So it's sort of that measure, that deviation away from a sort of rest state. In quantum mechanics, yes. In mechanics, no. Yeah. So, no. What I do want to draw people's attention to is that it's mass times velocity. Okay? So because it's mass times velocity, velocity is a vector, so momentum is also a vector. It's a vector quantity, all right? It has size and it has direction. So in particular, if we're talking about two things that are moving in opposite directions and they're the same mass and the same speed, their momentums are opposite. So it's good to keep that in mind, and that will be something that we touch on before later as well. Photons don't... What is happening? They can't hit you. They can. It's called sunburn. Despicable Me vector introduction video in school. Thomas, when I was in school, Despicable Me wasn't out yet. I think. No, it definitely was. Was it 2010? Bloody hell. Terrifying. Cat, you're old but not that old. But like in my head, the hype of Despicable Me is definitely like post-school era. When did Despicable Me 2 came out? Okay, Despicable Me 2 came out when I left school. So like not that far off. In Scotland, you can get burned from hearing the word rumours about the sky. Oh, 2010, you were at uni. Jeez. Is that... Yeah, the continual game of someone younger than me is insert how old and was born when. Horrifying. Okay. So momentum is a vector quantity which has a size and direction. And it's just gone to an ad break, which is really annoying. This is what we get for chatting too much. Can I do anything about this? No. You were in primary school. I was definitely not. Would have been year 8, I think. No, 9. But I also left school at 16 rather than at 18 because I went to a college. So I have like fewer years of proper schooling. I'm half wondering if now is a good point to do a little vector summary. Still start a PhD at your age? Yes, you can. And you should. PhDs at any age. That's what we say. Do it! Okay, let's do a little... vector recap. Okay, so this is just a very, very, very brief overview of the bits of vectors that we're going to need for this. At some point in the future, I'll do a more vectors from a calculus, from a actual intentionally caring about it little area. But typically vectors are represented as arrows, and that's because we can think of them as quantities that have size and direction. So vectors typically written with underlines and drawn as arrows are values, things which have both a magnitude and direction. E.g. speed versus velocity. Okay, so speed is a scalar quantity. So scalar is size only. Whereas a velocity has a speed attached to it, it has a size attached to it, but it also has a direction. So a car moving at 30 miles an hour, its speed is 30 miles an hour, but if I impose it's 30 miles an hour north, then it has a direction. Now we don't use north, south, east, west when talking about vectors normally. If we did, they would be called bearings, which is more of a seafaring thing, and something that I still don't understand why it's in GCSEs, because we don't really use it anymore, but the idea that all children are going to be lost in the woods at some point in their lives, so definitely need to know how bearings work, amuses me. But typically, we talk about Cartesian vectors. So we only really care about X, Y, Z. Coordinate systems. Which there are better ways or different ways to describe vectors than just this basis. But for our purposes, this is, I'm going to do 2D for the minute. If I have my XY grid here, you got to draw a little arrow to indicate a vector. No, I refuse. I have this when I was teaching Mechanics 1 in Bath every year. I would have a fight with the undergrads because I'm like, I'm sorry, I am underlining it. I don't care what you say. If I'm typesetting it, it's bold, and if I am writing it, it's an underline. I refuse to do like that one or that one, or like trying to make my handwriting bold. I'm not doing it. All of those can go away. I am underlining. Okay, so if we have a vector in space, so going back to like this one that I drew before, A, the way that A is written, it has two components. It has a horizontal component X and a vertical component Y. And we say that this vector, corresponding to this arrow, if I draw the exact same thing over my grid, I start at 0 and I end at a point here. That point has some coordinates, right? So AX and AY. And those coordinates correspond to the values on this axis, or these axes. So we're probably all quite familiar with coordinates. Vectors are a way of writing that. So this is that vector. So A is AX, AY. Or we might write it vertically. Or AX, AY. I'm not going to put equals. Or a secret third option, which is any number in, any number in the x direction is that number times 1. So we sort of encode the direction with this value I and then j. And we say that I is 1 in the x direction and j is 1 in the y direction, which means that we can write the vector as the value times the direction, and then the value times the direction. And that's a way of sort of breaking it up into its elements, right? To get to our point A, we have to go AX in the horizontal and AY in the vertical. Those are the different ways of writing vectors. Whenever we do adding and subtracting of vectors, we write them in this A, I, and J basis. If we were going to do 3, so I and J, we add K in for the Z direction as well, which, if I draw out my grid again, my axes again, so I have my X, my Y, and my Z, I now have I takes me a distance 1, called a unit, away from the origin in the X direction, J takes me a distance 1 in the Y, and K takes me a distance 1 in the Z. And a given point in space P is going to have some value, I've already used A, some value X in the I direction plus some value Y in the J plus some value Z in the K. So this is how we write vectors, and we can add vectors by adding all of the bits that have an I in front of them, adding all the bits that have a J in front of them, and adding all the bits that have a K behind them, not in front of them. That corresponds to sort of this vector here. There's a whole other realm of things here. If we talk about the size, we talk about the length of the vector. So the size, magnitude of a vector is its length, or straight line distance, because the shortest distance between 2 points is the straight line connecting them. Fun little geometry axiom for you there. Not axiom, I think theorem. Unsure. Fun fact. So for my vector A, I have AX and AY. Then we say that the magnitude of A, which we denote with this modular sign, is basically the inverse Pythagoras' theorem. A squared, this length distance here, which is this bit, that's the size of the arrow, is that squared is AX squared plus AY squared. So squared is AX squared plus AY squared, which gives us that the size of a vector is the square root of the square of its sides. I appreciate this is very speedy. There are other resources out there for more in-depth vector stuff. I think I've done a lecture on it somewhere way back when in the VODs. Should still be on Twitch, maybe. But for all intents and purposes, this IJK notation and the size of a vector is all we're going to really need today. But essentially, yeah, they have direction, they have size, And it's just a lot of triangles and trigonometry. Looks a lot like Pythagoras. It's always Pythagoras. That bastard got everywhere. Yeah, you essentially say if I want to work out the length of the vector and I draw the length of it with how long it is, that's what it is, because these are always going to be at right angles to each other, so you always have this right angle triangle sort of going on, where this is my vector, and this is its y component, and this is its x component. So that's where that comes in. If we wanted the size of the 3D vector, we would also be adding in the square of that element as well. But that starts getting a bit complicated, and I don't think any of the stuff we're doing today needs it. So that's there too. Ta-da! Spoilers. So, back to the thing that we're supposed to be talking about. In summary, momentum has a magnitude and a direction. It's always the same as motion. Okay, so if I have positive momentum, I have forwards momentum, I'm moving forwards. Because of this equation where mom is mass times velocity. Mass is a scalar, and velocity is the vector. So the vector bit is the bit that hides the direction, and my velocity is always the same direction as my travel. So my momentum is always the same as my travel, but I've scaled it with my size. So if I'm traveling at 1 mile an hour, 1 meter per second, forwards, I multiply that by my size, and now I have my momentum, which is my mass times 1. Speaking of things we should talk about, let's quickly introduce the L2 norm. No. The word norm is banned. Okay. Where on what? Stop it. I don't know why that happens. Okay. Moving onwards a little bit. If a force is applied to a body for a length of time, it's always really weird writing out the abstract sentences that make sense in maths when you know where you're going, but just out of context is a weird thing to say. It will have some effect on its momentum. Okay, so this is Newton's first law. At rest, stay there. In motion, stay there. Things don't like changing. Okay, change is scary. Mood. So things that are unaffected by a force will just continue as they are indefinitely. However, if a force is applied over a given length of time, if a force is applied, it's going to have an effect. We quantify it as a given length of time. This is why gravity is sort of not in this specific system of like what I'm about to talk about, because the length of time is infinite, like is always there. It's a constant force. So quantifying it in this way doesn't make sense. Before someone calls me out for why it's not there. So we quantify the effect called impulse. As we call it, I is the force times the time. Okay? A guy called Norm calls walks into chat and gets me. No, I would never. I would never. The mods might. I would never. Yeah, so the impulse, an impulse is a force applied for a given time. So a large impulse might be a large force over a long period of time. It might be a large force over a really short period of time. But it's essentially the quantifying the effect of like a prod for all intents and purposes, or a collision, or like a click. And specifically, the impulse is the change in momentum. Okay, so if something has a given momentum, it's moving with some velocity in a direction, and then I look away and I look back and it's now moving with a different velocity. Something will have had to happen to cause that velocity shift, right? Because Newton's first law says that bodies in motion stay in motion. They say that without an effect, things aren't going to happen. So something must have happened, and an impulse is a measure, like, is the thing that occurred. Flip side of that is if I poke something that's either moving or not moving, that's not going to change its mass. It's not going to have an effect on the mass of the object. So it's going to affect the velocity. Okay, so just saying that out right. Since a force on a body won't... When I was writing these lecture notes, I had like many crises about whether it's affect or effect. If I'm wrong, just correct me, because I'm still not convinced. Since a force on a body won't affect the mass, it must affect the velocity. Affect is a verb, affect is a noun. So it is affect in that case. Yes, because it's doing. Yes. Good. This is secretly a way to teach me grammar. Is that formula measuring the change in momentum or the rate of change in momentum? The change in momentum. So it's just the difference in momentum, which we can show by the impulse momentum principle. Okay, so it's just, at the minute, all we know is impulse is force times time, and I'm telling you that it's an effect, change in velocity. So I would like to pose to you, if we begin... I'm going to do some calculus, by the way. This is a calculus warning. I don't have an alert for it. I have... What can I do? I'll do that. But instead of dual, it's the word calculus. Is that a thing? Let's do that. Sorry if that was a jump scare to anyone. That was very loud to me. You must always expect the Yu-Gi-Oh! Because it's there. It's lurking. Okay, impulse momentum principle, which says, if we begin with Newton's second law, which, for those who aren't sick of it yet, is force is mass times acceleration. Okay? And acceleration is something that varies over time, and force is something that varies over time. Mass is pretty fixed. We're not talking about something that's decaying. It's a fixed for time. I can also write acceleration as the rate of change of velocity. So a of t is actually dv dt. Okay, it's the derivative of velocity. I take the velocity, I calculate its derivative, that gives me its acceleration. And this goes back to something that we touched on ages ago, with our kinematics, which was you have that your position in space, you take its derivative and you get its velocity, and you take its derivative and you get its acceleration. So this is dx dt, and this is dv dt equals the second derivative of space, d squared. I have a question. If I hit a rock with a hammer, the rock splits into many pieces, hence affecting the mass of the rock. How do I deal with that? Good question, Banana. So, sorry, I shouldn't sound so surprised. So essentially, when we say it won't affect the mass, we're talking about the entire system. So at that point, you would start with the total mass of the rock, and then your after mass is all of the pieces combined. So if I have two, say the rock splits in half, those two halves will sum to make the whole rock back. And the velocity of those two halves should, and the hammer, technically, those three bits, hammer, half rock, should sum to rock and hammer. And I wrote a question, I nicked a question from the internet on that topic later. I say should because, like, friction and also rocks don't split perfectly evenly. There's going to be some, like, gravelly nonsense going on. But for all intents and purposes of idealized collisions, they should sum to near enough exactly that. It was pretty cool. Similarly with things that collide and stick together afterwards, you talk about the within a closed system, essentially. Okay, so we have force is mass times acceleration. Acceleration can be written as the rate of change of velocity. So I have that my force, which is a function of time, is mass times the derivative of velocity, which is a function of time, with respect to time. Then I do some sneaky things where mass doesn't change with time. So I write my force is the same, like the rate of change of something that doesn't change with time is pretty chill. So I can just take my derivative out and I have my mass times velocity. I'm also going to do something a bit weird. And for notation purposes, to make my life easier, I'm going to say P is momentum. Okay, so I have F is d dt of P. So force is derivative with respect to time of momentum. Pretty cool. So force is rate of change of momentum. But I can also go one step further, and I can integrate this out. And I can say that, so integrating both sides, you get the integral of force with respect to time is equals to the integral of d dt p dt. So those of you that have done integration before will know that if there's no, there's no like limits, so I'm not looking at a measure over two specific points in time, I have to add in constants. What I'm going to do is cheat that, and I'm going to say from 0 to some time t. From 0 to some time t, which might be like 1 in the future. Bear with me at this point. People that really are interested in this, go for it. Everyone else, chill. What that tells me, so I integrate out this is force, so it's F times time. Can we cancel the dt? Shush. Gotta multiply the dt to the other side. Shush. So we get force times time. And here I get p evaluated at t minus p evaluated at 0. Or equivalently, force times the length of time over the impact is momentum after minus momentum before. Come to the dark side, become a real physicist. And if you'll notice that this is impulse, right? This half of the equation is impulse. So we can say that I is momentum after, which I'm going to call mv minus mu. Velocity after velocity before. So that is, this was hand wavy, but does track, I promise. But is essentially the proof of the impulse momentum principle. In my master's thesis, diploma, I had a language spelling crisis over axis, axes, access, excess. I don't fault you. Valid. Absolutely valid. Axes as a word upsets me greatly. I just don't like it. I don't like how it's spelled. QED. I don't know what our initial state was, but that's my proof. So I equals mv minus mu is going to be really useful, and also ft is mv minus mu is also going to be useful. So when we sort of do our summary at the end, I will write those two out explicitly. The final thing before we jump into a little bit of a break is the principle of conservation of momentum, which is a friggin' big thing. So, for a given collision, of two or more-ish mass-full bodies. Remember, we're only working with things that move and have mass here. Things that don't have mass, don't move, don't exist in our brains. The principle of conservation of momentum. No, fit. Okay, which sometimes is called PCOM, PCM, or how I write it, which is ConMom, because, spoiler alert, fluid dynamics is all conservation rules, so conservation of mass, conservation of momentum, so ConMom, chef's kiss. Is massful a word? No. Massful is most definitely me making shit up. I've used massful in this context to say bodies with mass. But principle of conservation of momentum for a collision says that momentum before equals, I should have done this in purple, actually. Mom before equals mom after. I have had the realization that if chat try and write a word that has, try and write the word mom, I think it's going to get caught by the auto thing, just as a heads up. Yeah, John, if you want to ask questions at any point, do please feel free, because otherwise I just keep going. If you're also just vibing, vibe. Yes, it will, and no, you will not get exceptions. Yeah, basically. Sorry. Certain parental words have to be banned for cat sanity reasons. Whoop whoop. I'm vibing just horribly. I feel like that's in your name though, so I don't know how much me interacting with that is going to make a difference. Gonna say comment all about making you momentum. You know what? I back it. Part of the brand, family name. Love it. Okay, so, principle of conservation of momentum, Con Mom says, momentum before is momentum after of the total system. So whatever I define as part of the system before a collision has to be included after. If I hit a nail with a hammer, the momentum before is both the hammer and the nail. I can't then say, oh, and look, it's different because the nail is stationary afterwards. You are talking about two objects, more objects, the total masses, the total velocities, and if they break apart or separate or conjoin, you have to still consider both of them. They might have the same velocity afterwards if they have attached, or they might have two different velocities afterwards if you break something apart, but it's the total system. So in the case of two object collision, the momentum before equals momentum after might be, for bodies A and B, that's MA UA plus MB UB is equals to MA VA. Here I'm using U and V to be before and after. Remember the Suvat equations, that's where that's coming from. MB VB. Okay? And then the other fun fact, because Newton's laws, you can never escape them, this is why we did them so early. N3 says, because every force has an equal and opposite, every action has an equal opposite reaction, that one. Two bodies, exact impulses. This is one of those sentences that I'm like, Twitch, behave yourself. The two bodies' exact impulses on each other of the same magnitude and opposite direction. Okay, so if two things sort of collide, the pushback is going to be identical. Okay. And remember that those velocities, those momentums, might be vectorized. So we might be talking about something coming in at an angle. The equal and opposite will be in the same direction as the initial travel. Okay. In summary, before we jump to the thingy part of this, so before we jump to questions, we have that momentum is mass times velocity. We have the impulse is force times time. We also have the impulse is the measure of change of momentum. Now remember, something impacts impulse, it causes an impulse on the other. I'm really not sure what the grammar there is. So this one is mv minus mu, right? Difference between the two, final velocity, final momentum minus the first. And then we have the conservation of momentum, which is m1 u1 plus m2 u2 is m1 v1 plus m2 v2. And then finally, just really quickly, for a given x, y, and z, a vector p will have some amount in the I direction plus some amount in the J direction plus some amount in the K direction, and the size of that vector is the square root of the different directions squared, a squared plus b squared plus c squared. So that essentially is the topic for this chapter, for this lecture. So momentum, impulse, principle of conservation of momentum, and impulse momentum. There was a word there. I forgot what the word is. And vectors. So we're going to take a quick break. I'm going to stop talking for like a few minutes. What time is it? We'll be back at 1:15 the hour, I think. Around about then. So I will see you. And then I have I have 4 exam style questions, one of which involves a hammer. So yay. So I will see y'all shortly. So, question 1. 2 particles, A and B, have masses 4m and m respectively. The particles are then moving towards each other on a smooth horizontal surface, so we're given smooth, so no friction, and collide directly. That seems to be the buzzwords for not an elastic collision. The speeds of A and B are 2u and 5u before collision. Immediately post-collision, the speed of A is 0.5u and its direction of motion is reversed. Remember, momentum has direction, velocities have direction. Find the speed and direction of motion of B post-collision. So, as with basically all questions, I like drawing it out first. Spoilers. We'll see. So, my gut reaction is always to draw everything. So I have my 2 particles, A and B. Okay, and so I'm going to have like a before collision drawing. And an after collision drawing. Okay, so before and after. So before collision, we're told that they're moving towards each other, which is important to know. And this has a mass 4m, and this has mass m. Actually, I'm gonna just pull... Where do I want to put this? I'm gonna put it there. Because I want to draw the forces, I think, to put... So that has mass 4m, that has mass m, that has mass 4m, that has mass m. Before they're moving with speed 2u and speed 5u, but obviously their velocities are in different directions. And then we're told that the speed of A is 0.5u and its direction is reversed. So now A is moving to the left with some speed 0.5u. And we don't know what's happening with B. One thing that's important to do as well is to define which direction is positive, and because we read left to right, we tend to set positive towards the right as well. So in both cases, I have to have positive in the same direction, so they're both going to go towards the right. So the questions I'm asked are find the speed and direction of and motion. So the questions I'm asked are find the speed and direction of motion of B post-collision, and find the magnitude of the impulse exerted on A by B. So I don't know which direction B is moving. I'm gonna chuck an arrow this way and say it's moving with some speed V. V could be negative, at which point the direction of motion is back towards the left, or V is positive and I've guessed right that it's towards the right. They could both be, if you think, I don't know what a good example of this is, but essentially if this is stationary and this is moving, and I hit, and now they're both moving in that direction versus sort of a coming together and going apart, it is possible. So because we've defined to the right as positive, the positive or negativeness of the velocity of B will tell us which direction. So in part A, we're not given anything about impulse, we're not given anything about time. We just have some momentums before, some momentums afterwards, but we don't have velocity afterwards. So we need, for part A, the con mom. which says that MA UA plus MBUB is equals to the afterwards as well. So after collision VA, MB VB. So the mass of A is 4m. This question is also quite nice because it keeps things in m's and u's, which sort of gets rid of them. So that's, and then times that by the speed, so 2u. And then this one is m times 5u. So that's our momentum in the system beforehand. Those two balls are moving with those directions. I've already made a mistake because the 5u here is in the towards the left. So what I should have done is said that, right, so we have m times, and now the 5u is to the left, so it's negative, so it's minus 5u. So we encode direction with positive and negative, right? Is it moving to the left? Is it moving to the right? Then we have this one, so we have 4m, and now we're moving to the left again. So this is minus 0.5u plus mv. So v is the thing that we're trying to find. What is v? What is the speed, the velocity of b after the collision? Simplifying this out, 4 times 2, so we have 8 mu minus 5 mu is equals to minus 2 mu plus mv. So cancelling that down, we get cancel through all the m's first. They're not going to be involved in the speeds. So 8 minus 5 is 3. So we end up with minus 3 over minus 3u add 2u equals v minus u equals v. No. Yes. No. As you can tell, it is officially... Why does that keep happening? That point in the evening where I am exhausted. Let's try that again. Right. 8 mu minus 5 mu equals 0.5 times 4. Half times 4 is 2. Minus 2 mu plus mv. Cancel through all of the m's. 8 minus 5 is 3u. Add 2u equals v. So I've taken that minus 2 over. So I get 5u equals v. So the speed of b, or the velocity of b after collision is 5u to the right. Now, if I had defined all the way up here positive to be to the left, then the value I got out would have been minus 5, so it would have been opposite to the direction that I have said is positive. So still going to the right. Part B then, find the magnitude of the impulse exerted on A by B in the collision. So now we want impulse. We now know the momentum beforehand and the momentum afterwards, but we're looking at on A by B. So I have the impulse now of just one of those bodies. So I have mv, which is afterwards, minus mu, which is before. So on A, so that's going to be 4m times the speed beforehand, afterwards, sorry, which is minus a half u, or 0.5u, minus 4m yes, sorry, 2u, speed beforehand. So this is looking at A. So 0.5 in the negative times 4m, and then 2u in the positive times 4m. Solving that out, you end up with minus 2mu minus 8mu. So you end up with minus 10mu. And then we'll put in our units because that's good for us. Meters per second to the minus 1. Having m's and meters per second is always a little bit confusing, but we'll pretend that we know what's going on. A big ball of mass m hits a small ball of mass m, which gets reflected by a wall and gets hit again by m. How many times do the balls collide? It depends on the size, and there's a really cool 3 blue 1 brown video about how when you have the bigger one tending to a very, very, very large size, the number of collisions you end up getting is pi. Or like the digits of pi in thousands or whatever. And this is because of a really cool thing that I thought about doing for this lecture, and then I did the maths of it, and you need phase spaces, and suddenly it gets quite complicated. But there is a really, really cool 3 blue 1 brown video about it. And also, if you are someone like me that likes like clicky sounds, like keyboard clickies, it's 2 blocks, and when they collide, they make a little click sound, and I find it very satisfying to listen to. I just think it's a really cool video. Highly recommend. Shout out Grant Sanderson. Yeah. Honestly, kinda is really satisfying. The thing is though, when you have this sort of like massive small block wall, obviously the distance between the two gets really, really, really small, and then they kind of like start the distance between the sounds gets shorter and shorter. So it kind of has this like very large. Go watch the video. It's really cool. Okay, so that's that question. Question 2. A particle of mass 0.5 kilograms is moving with velocity 4j meters per second. And here j should be a vector. Immediately after the impulse, it then receives an impulse I newtons. Newton seconds. Immediately after the impulse, the particle has velocity 2i plus 3j meters per second. Find I and then find the magnitude of I. So find the vector of the impulse and then find the size of that vector. So starting with part A, we have a particle, we have an impulse, and we have a before and after. So when we're talking about collisions, conservation of momentum comes up. When we're just talking about the effect of one particle, tends to be the impulse momentum principle. So we have I is mass times the velocity after minus mass times the velocity before. So I here is 0.5 times after, which is 2i plus 3j, minus the mass, which is 0.5, times before, which is just 4j. So I'm going to write 0i plus 4j, just so that I can keep track. I can keep track. Get it? Get it? Sorry. Of what I'm multiplying and adding together. So expanding these brackets out, 0.5 times 2 is just 1, so I get I plus 3 over 2j minus 0i minus 2j. Then when we're adding vectors together, we add the i's together and add the j's together. It's kind of like when you do quadratics, you add the terms, like terms together, right? So all of the x's get clumped together, all of the y's get clumped together, all of the x squareds get clumped together. We can add them. So I minus 0, 1 minus 0 is 1, so that's just I. 3 over 2 minus 2 is minus a half j. So my impulse is I minus a half j Newton seconds. Two large Australian flight birds of mass M and velocity Euclid, they're emus. That is awful. 10 out of 10. Okay, and then part B, find the magnitude. So now we want the vector, and technically this is a vector, so I should be underlining it, but then it starts getting a bit disgusting to look at. But remember what I said, that it's, you take the elements, so the coefficients of the i's and the j's, and you do the square root of the squares. So the coefficient in front of the I is 1, and we square it. Add the coefficient in front of the j, which is -1/2, and we square that. So we don't have to worry too much about squaring negatives or taking the square root of a negative. This is a size. It shouldn't be complex. If it is, something has gone disastrously wrong. So we have the square root of 1 plus 1/4, which is the square root of 5/4, which is, taking that out, half root 5, which is about 1.1. I think that's right. The 1.1 bit, not everything else. I'm pretty confident on everything else. 1.5 times square root of 5. 1.118. I'll take that. Cool. And if we wanted to talk about the direction of it as well, we could start calculating the angles based on the tangents. But we're not asked to, so we're not going to. So there. Part 3. If I am speeding through these and people do have questions, obviously please do ask. You are always welcome. No dumb questions. Sometimes dumb streamer, so. Now I want to create an exam question where one object vanishes perpendicular to reality. I mean, I have seen, you do a question from a frame of reference that's in 2D. So you talk about seeing something move in 2D space, and then it disappears. And the question is why and how, and the answer is 3D. So it's not like infinitely far off. You know, it's not impossible. Would be a fun, and I think I say fun, it would be a mean question to ask in an exam of like, how has this happened? And the answer is, it's secretly 3D. But I wouldn't be surprised to see that either. Yeah. Okay, question 3. Two particles, A and B, with masses 3 kg and 2 kg respectively, are moving in the same direction on a smooth horizontal plane when they collide directly. Immediately before their collisions, their speeds are 4 and 1.5 meters per second, respectively. The word respectively pops up a lot in this, is what I'm learning. And in the collision, they join to form a single particle C, find the speed of C. So once again, doing our little diagram, we have A and B before, and then we have A and B afterwards. So A, B, and C. And we're told that they're all moving in the same direction, right? The two bodies are moving in the same direction to start, and then the combined particle is moving in the same direction afterwards. So let's put direction of motion as positive. Shouldn't need to worry too much about negatives, but good to know that if we end up with a negative speed of C, we've done something wrong. We're told masses. So the mass here is 3 kilograms, this mass here is 2 kilograms. And then the mass of C we're not told, but we're told that it's the two particles combined. So we have that it's 3 plus 2. So the mass of C is 5 kilograms. We're told their speeds. So the speed of A is 4 meters per second, and the speed of B is 1.5 meters per second. So if A was moving slower than B, it would never catch up because they're both moving in that same direction. And fun fact, with that block stuck between big block and Infinite 1, that's when collisions stop, is when the thing on the outside is moving faster than the thing on the inside because it can't catch up. There's no opportunity for it to catch up. And the question is, what is V here? So we're not given any impulses, we're not given any times. Nothing's really changing, so it's conservation of momentum again. And this is momentum and impulse. Once you start doing them, it's only really 3 equations you have to worry about. 2 technically, conmom and impulse. So it becomes quite like nice to do. It's just very procedural. So conmom here is MAUA plus MBUB is equals to, so now A and B are combined to make C, so it's the total mass times whatever the velocity of that total mass is. So we could write it as MA VA plus MB VB, where VA and VB are the same. This is a nicer way to do that, right? That is, if that is MA plus MB, that is equals to VA equals to VB, because they're going to be the same, because they're the same object. Then we just plug in our values. So we have 3 times 4 for A, plus 2 times 1.5 is equals to 5 times V. So 12 plus 2 times 1.5 is, 1.5 is 3 over 2 times 2, that's 3, is equals to 5V. So that's 15 is 5 times V, divide through both sides by 5, and you get that V is 3 meters per second. So once you figure out what is happening with the physical system itself, like the diagram, and figuring out which direction things are moving in, the nice thing about conservation of momentum and impulse equations, the algebra that you have to do is quite nice. And I'm going to say quite nice because I think it is. The main concern is going to be making sure that you have consistently defined positive motion, or consistently defined the sort of frame of reference you're working in, which basis, which way's X, which way's Y, that sort of thing. And I am just going to skip this song because I really don't like it. I feel like there could be very real implications here which would violate ideas like conservation, since you no longer really have a visible closed system. Yes. Hey, seriously, how's it going? How you doing? We're doing some mechanics. I hope that's okay. Food Acquired made chicken burgers. Nice. Enjoy. I ate before streaming, which eating at like 5 o'clock was a weird vibe, but it worked. Still alive, love mechanics, love that for you. Love that for you. Well, you are just in time for our 4th and final question, which is, ooh boy, a bit much. So, this is the question where, when Banana asked about hammers earlier, I got really excited because I feel like this question does kind of cover it a little bit. A tent peg is driven into soft ground by a blow from a hammer. The tent peg has mass 0.2 kilograms and the hammer has mass 3 kilograms. Immediately before the impact, the hammer has speed . There you go. Immediately before impact, the hammer has speed 16 meters per second, which needs that one. It is assumed that after impact, the hammer and peg move together vertically downwards. We're not assuming it's sort of bouncing up, we're assuming that it is a driving force straight through. Find the common speed of the peg and hammer, and then until the peg and hammer come to rest after 0.05 seconds, the ground exerts a resistive force, which is assumed to be constant and of magnitude R newtons. Find R. So again, having sort of a diagram for this, we have our peg and our hammer, right? We're assuming the peg is stationary, So this has mass 0.2 kilograms and 0 meters per second. This has mass 3 kilograms and is moving with 16 meters per second downwards. So I'm gonna, in this case, put positive to be down. We're only assuming vertical motion. We're not assuming sort of horizontal. The swing is not horizontal here. It's straight down. And then you have the impulse. And now what you have is the hammer and the peg moving as one unit, right? This is now one body, which is moving with 3.2 kilograms as an entire entity, and we've been told to find V. Where here sort of a collision has happened. So there's this immediate impact. Then we have that entire thing, so the hammer and peg combined, take 0.05 seconds to move through the ground, right? So there is some ground here throughout all of these. Ignore my handy dandy right, so it has moved vertically downwards. And there is some resistive force here, R, pushing against it, because it's moving through the ground is pushing back against it. Think of it like drag in the air when something's falling. But we're talking over that entire body, right? So after this force has been applied, this resistive force, now the hammer and peg is still 3.2 kilograms, not kilometers, and now it's at rest. So until it comes to rest, so it's now moving with 0 ms minus 1. So we have sort of instant collision, hammer and peg becomes hammer and peg. You know the song Pen, Pineapple, Apple Pen? That's what's happening in my head with this question, right? You have pen, you have peg, and you have hammer, and now it's the peg and the hammer is one thing. Then we have an impulse applied, and then we have it's further down. So there's a few different steps. So the first part A, focuses on that first instantaneous collision, and the second one focuses on force being applied over time to cause motion to come to rest. Fun fact, impulse in German is Stob, momentum is impulse, not confusing control. That is not helpful. God damn it, Germany. Okay, so part A. Find the common speed of the peg and the hammer. So pre and post collision, we're going to use Cotton Mom again. So MP UP plus MH UH is M P plus H V P plus H, okay? P for peg, H for hammer, P plus H for the combined. So 0.2 times speed of the peg, we're assuming is initially 0. It's not randomly moving on its own. But we have this massive momentum coming from the hammer. So we have 3 times 16 from the hammer. Then we have the sum of the two masses, so 3.2 times V, and we don't know what V is. So 3 times 16 is something that I haven't written down, which is so useful. Can I do it in my head? It's 30 plus 6, 18, it's 48. It is 48. So 48 is 3.2 V. So V is 48 divided by 3.2. Is this going to go nicely? It is! It is 15 meters per second. So that the hammer and peg immediately after collision is moving with 15 meters per second. So you've lost a meter per second from that collision. To pick up the mass of the peg with the hammer motion, you've lost 1 meters per second, which is actually really cool. That's a fun That's a fun fact. I enjoyed that. Okay, part B. Part B was until the peg and hammer come to rest after 0.05, the ground exerts a resistive force, which is assumed to be constant. So, I think we want, first of all, the impulse, which is force times time. So the forces at effect here are, you have the peg and hammer, right? You have gravity working downwards, and you have resistance to motion upwards. So those are the two forces in effect from the continual motion. So I said downwards was positive, so that's 3.2 g minus r are the total forces in effect on the thing. And it's applied for 0.05 seconds. I'm not going to solve that immediately, I'm just going to leave that there. I'm then going to do impulse is change in momentum. So now we know that the starting speed from this 0.05 is 15. So mv minus mu. The final speed is 0, right, until it comes to rest. So 3.2 times 0 minus 3.2 times 15, because it's this section that we're looking at. So we're moving here with 15 meters per second. Then we can set those two equations for impulse to be equal to each other. So now I'm going to plug this in here. Okay, because impulse is equal to impulse. So not too bad. So we have 3.2 g minus r times 0.05 is equals to 3.2 times 0 minus 3.2 times 15. Well, we just did 48 divided by 3.2 is 15. So I know that that value is 48. I know that that value is 0. Don't ask me why I worked backwards for this. 3.2 times 9.8 is 31.36 minus r. That was the weirdest r I've ever written. 31.36 times r. Times 0.05. Tidying this up, I end up with 31.36 minus r is minus 48 over 0.05. So 31.36 minus r is equals to minus 960. Taking the r over to the other side, add the minus 960 over to the other side, I end up with 31.36 plus 960 is equals to r. So r is equals to 991 to 3 significant figures. And that is in newtons. So that's a lot of force, right? That's for a pretty fast moving hammer and a very small peg, 10 peg. That is quite a lot of force applied. But this is where this style of question I think is really, really nice, is because you have that pre and post collision of the hammer hitting the peg to make a whole new object, and then you have the impulse of the object on the ground. So you have to separate those two things out into 1.5. You can't start from the far left-hand side to get to the far right-hand side. Or you can, but you're making work more complicated for yourself. So this nice gradient between the two makes the equations quite lovely. So, in summary, my voice is gone, by the way. In summary, we started with momentum and impulse. We gave a very cheeky definition of it by me hand waving a lot, but basically said that momentum was equal to mass times velocity, measured in Newton seconds, which is a cool unit, in my opinion, and essentially quantifies the amount of force required to bring an object to stop, or the amount of drive something has to go forwards. It's a vector quantity, so we did a very brief recap of vectors, specifically looking at Cartesian vectors and its XYZ components, how we write them with unit vectors ijk, which are length 1 in the base axes directions. And also quickly touched on how you quantify the magnitude of those vectors, so the size of those vectors, which is, it all comes back to Pythagoras. It's always Pythagoras. That dude put his name everywhere over geometry, essentially. It's very rude. Then we talked about impulse, and we said that impulse was the change in momentum and the force applied over a certain time. It's that measure of that force over a certain time and the effect that it has on the momentum. We then talked about the impulse momentum principle, which states, and we did a little derivation using a cheeky bit of calculus, cheeky bit of integration, essentially to get to that the impulse, if it's the change in momentum, it's the momentum after the impulse has happened, subtracted by, or minus the momentum before. And we can set those two things to be equal. Force times time is momentum after times momentum before. So depending what we call length of time, we can be quite sneaky with how we use this equation. Finally, we jumped back to the principle of conservation of momentum, or ConMom equation, which just says that in a system, in a closed system, momentum before is equal to momentum afterwards. So when we talk about bodies either coming together or separating, say when you split a rock with a hammer, you have to be careful about what you consider to be part of the system beforehand and afterwards. So you can't lose momentum without some extra stuff happening. And for our case, with bodies with mass, everyone behaving properly, it should all be pretty well behaved. That equation then is written MAUA plus MBUB equals MAVA plus MBVB. And then we had a quick little handy-dandy summary as hidden by my head. Yeah. Pythag took someone else's geometry and put his name on it? Yeah. Because that would never happen in academia these days. Yeah, so then we did some equations, so some questions. So we started off with two particles colliding on a smooth surface. So just looking at unidirectional flow. Then we talked about things coming in at different angles, and we looked at some vector equations of momentum and impulse, as well as quantifying the magnitude of impulses. Then we went back to what about two things colliding and sticking together? How do we compute that? And then we had a nice real-world example with a tent peg being pushed into the ground and computing the forces and resistance to motion in this case. And that basically wraps up this lecture. So next we talk about, with what we've been doing, we talk about collisions as being, thank you for the follow, welcome in, I hope you enjoy. Yeah, with this we've been talking about collisions being sort of, momentum is conserved, energy is conserved, everything's well behaved. But what about elasticity? So next time my plan is to cover, let me just double check that. Yeah, so we're going to cover elasticity, so that's things like Hooke laws, energy stored in springs, energy stored in strings, and then also going back to those collisions and saying, well, what about inelastic or elastic collisions? What about when energy is lost because of that collision? So that is going to be super hype. Can't wait to write the lecture notes for that one. And yeah, ta-da! I don't know how to close these things.